Hello, today we're going to talk about how to use parametric equations to model two-dimensional motion, and in particular this is motorized constrained motion, which is different from the type where you're just throwing an object, a projectile, and letting it fall by gravity. So here's an example. Lucinda is on a Ferris wheel of radius 35 feet that turns at the rate of 1 revolution every 20 seconds. The lowest point on the Ferris wheel at the 6 o'clock, if you were like on a clock, the bottom of the clock, 6 o'clock position, that lowest point is 15 feet above ground level at the point 0, 15. So I just want to do a quick graph of this Ferris wheel. And here we go. Here's ground. And maybe let's say that's 15 feet above the ground. We'd have a circle. And let's see if I can get a circle to kind of show up where I want. All right, so that's probably not drawn to scale very well, but some point above the ground, and it's going around like this. All right, and so Lucinda's position can be modeled like this. If you think about it, as she goes up on the Ferris wheel, she's also moving to the left. And as she comes back down the Ferris wheel, she's also moving to the right, or she keeps going around, she's moving to the right, and then to the left and to the right. So she has left-right movement that is like this, 35 cosine. Actually, maybe she'd be going this way. And then she's also going up and down as she goes around the circle. And so her up and down movement is modeled by 35 sine of something. And then it's got this plus 50. Well, if you think about it, sine varies between -1 and +1. So when sine is -1, this would be -35, which would be below ground. And we want the lowest point to be 15 feet above the ground. So we're going to take that low point of -35, 35 times -1, and we're going to add 50 to it. So -35 plus 50 is 15. And then the high point on the circle will be when sine is at its maximum. Sine can be as much as 1. 35 times 1 plus 50 means that at the top of the Ferris wheel, you're at 85 feet in the air. And so this description right here describes her trip around the Ferris wheel. Why is it pi over 10? Well, it says that she does 1 revolution, the Ferris wheel does 1 revolution every 20 seconds. So this is our period. Our period equals 20 seconds. And then the whole thing repeats. And then if you remember in the formulas for sine and cosine waves, the b value here is 2 pi over the period. So we get 2 pi over b, or 2 pi over the period is 2 pi over 20, which is pi over 10. That should be the period. And that equals b. So our b value is pi over 10 in both cases. All right, so let's graph this on our calculators and just see what we see here. Oops, let's see, I need to erase some of my writing. Okay, so we have 35 cosine pi over 10 t. And by the way, anytime you're doing a graph with sines and cosines, you need to be in radian mode. So I'm going to check in just a minute and make sure I'm in radian mode. 35 sine pi over 10 t plus 50. All right, and then, mode. Let's make sure I am in radian mode. I should be in parametric mode. And then we're going to go to our window settings and just think about this. All right, so T min 0, T max. Well, I know it takes 20 seconds to go all the way around the Ferris wheel, so I'm going to pick 20 seconds to be the maximum. That'll give me a 1 complete trip around. T step can stay 0.1. X min. Okay, if I look at my X function, it's going to vary between -35 and +35 because cosine can vary between -1 and 1. So I need to let my x min be, say, -35. But I'm maybe going to leave a little white space there. So I'm going to go a little bit lower and call that -40 over to +40 for my x. X scale can still be 1. That's just what you can't buy ones. All right, and then my y min is going to be 15 feet above the ground, but I think I'd actually like to see the ground, so I'm going to let y min be -5 so I can actually see the line for the ground level. And then my top point is going to be 35 plus 50, 85 feet in the air. And again, I want a little white space, so I'm going to just call that 100, just round that up to 100. All right, and let's graph this and see what we get. Okay, it looks like it could be a Ferris wheel. Not really, because it's kind of oval. The reason it looks like an oval instead of a circle is because my screen is rectangular. So to make it look proper, I'm going to zoom square. That's choice number 5, zoom square. And now it looks like a circle. Oh, it got confused because I pressed enter. Hang on. Quit. Let's try to graph that again. Okay, so now I get a nice Ferris wheel looking thing, and it looks like it is 15 feet in the air at the lowest point and goes up from there. And we can use our trace feature to watch what happens as she goes around. At time 0, she's over here on the side at 35 feet in the x direction and 50 feet up in the y direction, and we could trace it around. What is Lucinda's position from the ground at 0 seconds? Well, wait, I didn't go back and answer that. Okay, so at 0 seconds, she's 35, 50 is her position. I'll write that down here. At t equals 0, her position is 35.50. All right, and then it wants to know what happens at 4 seconds. So we're going to go back over here and do our trace. It's over to 4 seconds. We're counting by 0.1, so it'll take a little bit of time here. Okay, went too far. There we go. At 4 seconds, her position, you can see, is 10.8 and 83.3. And just as a kind of check, it says it takes 20 seconds to go all the way around. So at 5 seconds, which is a little bit more, I should be a quarter of the way around, and that does seem to be what's happening. So, okay, so back over here we can answer this. At t equals 4, her position is 10.8 and 83.3 feet. Her distance from the ground, then this would be it. 83.3 feet from the ground. All right, that's it for now. Thanks.